Okay, ladies and gentlemen, let's take a look a little bit further at differential equations. In this case, we're going to talk about separable differential equations. Now, for the Calc AB and Calc BC, separable differential equations are the only things we really care about. There are other ways to do differential equations, but that's a whole different topic, okay? Now, separable differential equations are literally what they say they are. They're things that you can separate. So just like the previous example where we got into some inverse natural logs, this isn't going to be quite so complicated. Okay, not going to be really quite so complicated at all. In fact, if I have y prime equals x squared plus 7x plus 3 all over y squared, this is really a fairly routine problem that can be done fairly simply. In this case, I have y squared times y prime because I can multiply both sides by y squared, giving me x squared plus 7x plus 3. Now, it might be a benefit to us to take a look, and instead of using the y primes, let's use a different notation. Y squared is dy over dx equals x squared plus 7x plus 3. And the reason these are called separables because that's exactly what we're going to do. We're going to separate this differential into two unique pieces. So I'm going to multiply both sides by dx, and now I have y squared dy equals x squared plus 7x plus 3 dx. And now I can integrate both sides, but what am I integrating this side with respect to its y's? So it's going to be 1/3 y cubed. And this side, it's going to be 1/3 x cubed plus 7/2 x squared plus 3x. Now, these are indefinite integrals, which means since I don't have bounds, I need a plus c somewhere. Well, the plus c is going to come into play on technically both sides, but whether I put plus c over here and plus c 1 over here, 2 over here, then put them together and call them C3, it doesn't make a difference. Why don't we just put a plus C over here, because there's a constant somewhere in this problem that is developed, whether from both sides or one side, but it's a constant. I don't know what the constant was to begin with, so let's just shove all the constant stuff to one side and call it C. Having done that, I come up with 1/3 y cubed equals 1/3 x cubed plus 7/2 x squared plus 3x plus c. Now, obviously, I can't leave it like this. I want to get y by itself. So to do that, I'm going to multiply everything by 3, and I come up with y cubed equals. Now, if I multiply everything by 3, that means I'm going to come up, like I said, y cubed over here. It's going to be x cubed here plus 21/2 x squared plus 9x plus 3c. Now, frankly, again, the 3 times c doesn't matter. If you so chose, you come over here and say, c1 equals 3 times c, because a constant times a constant is just going to be some other constant. In fact, it doesn't really make a difference. So I'm going to call this 3c and call it c1. And I want to get rid of this cube, so I'm going to cube root both sides. So I have y equals the cube root of x cubed plus 21 x squared over 2 plus 9x plus c1. Now, anytime I take a graph and I put this plus c on the end of it, if it's a basic and simple graph, that plus c is going to be a vertical shift. It's going to move the graph up, or it's going to move the graph down. So in the case of, if I were to have, for example, y equals x squared, if it's plus 1, the vertical shift is up 1. If y equals x squared minus 2, it's down 2. So what you have, y equals x squared plus nothing, that's right through the 0, you end up with an entire grouping of graphs based on the general shape, and in this case you have vertical shift only. Now, when you put the constant in here underneath the cube root and the whole 9 yards, it's going to cause a bit more problem than that. And so what you end up with is you still get a family of graphs, it's just not as directly connectable as a simple vertical shift. So in this particular case, you end up with a whole bunch of graphs that look like this guy. And so based on the value that C is, it could be a very simple swoop, it could be a much more severe swoop, or it could be a really crazy wild swoop. And if C gets big enough before long, it's going to look asymptotic. And so you end up with this. So you end up with a family of solutions, and that is a general solution. Now, obviously, anytime we want to go from a general solution to a specific solution, we have to know something. Well, if I tell you that at time or at x equals 0, y equals 5, okay? Now, we, by the way, tend to use time 0 pretty often, because if I plug 0 in for all of this, then it's going to become very obvious that 5 equals the cube root, that's going to go away, that's going to go away, that's going to go away, of C1. So in this case, you simply cube both sides, and you come up with 125 equals C1. All right. And again, that's going to be slightly different than the example in the book because they're still using a 3C situation. They also used a different initial condition. So depending on your condition, it changes everything. But the idea is still the same. You find a general solution, and you use an initial condition to find a specific solution. And the specific solution would be y equals the cube root of x cubed plus 21 over 2x squared plus 9x plus 125. In our case, that's going to be your specific solution. Now, that's with separable differential equations, where you're separating the x's and the y's. That's all that we're going to be doing for differential equations at this point.